So to motivate decision trees, let's suppose we're running a factory and you're the manager of this factory where you're trying to sort different types of citrus fruits. So you have lemons and oranges coming in, and then suppose you have like some conveyor belt that measures the height and the width of each of the citrus fruits, and your goal is to determine whether the fruit is an orange or a lemon. So one pretty natural way to do this, and which you've probably seen before in other areas, is something called a decision tree. So the way this works is we start at the top of the tree, and then we look at what the tree specifies in the particular node. For example, it might be asking something about a feature like the width, and if the width is greater than 6.5, we go to the left branch. If not, we go to the other branch. And then depending on which node you end up at next, you have another question, and then you go down another one of the branches of the tree. So this is the basic decision tree sort of setup, and throughout lecture today, we'll be talking about how you go about designing these sort of decision trees and learning the decision trees from data. So I guess this is a particular test example. If it turns out this example is less than 6.5 centimeters in width and less than 6 centimeters in height, then we'll end up at this bottom branch over here. And then the way a decision tree works slightly more generally is if you have a continuous feature like the height or the width, the way you decide which way to go is by checking whether the feature is greater or less than some threshold. And with this sort of decision tree, we come up with a decision boundary. So remember, this is a concept we talked about last week. Decision boundary sort of measures at what points your machine learning classifier ends up making different decisions. So you'll notice at the top node here, we have width greater than 6.5. If you plot the data points we have in feature space, then this width 6.5 corresponds to this vertical decision boundary here. So that's the first node in our tree. And if we just focus on this, let's say we focus on the right branch, height greater than 6. So the first branch tells us that the width is greater than 6.5. And this next one is asking whether the height is greater than or less than 6. So if the answer is no to the first one, we know we're on this left region here. And then the second thing is specifying this boundary here. So we end up having like axis-aligned planes that depending on which region the data point ends up, that's the label we end up assigning. Does a basic concept of a decision tree make sense? Like this is, yeah, go ahead.
Is it also possible to like have a function? So like it's not like having a straight line, it's possible to have a curvy line?
Yeah, that's a good question. You could, in this class we'll focus on axis-aligned ones, but you could imagine having trees that take into account combinations of different features. Any other questions? Okay, cool. Right, so this is just specifying what we talked about in a little bit more detail. We call each of these nodes. So nodes are the basically each point where you have to make a decision and evaluate a feature. Branching is determined by the feature value, and then the leaf nodes are our outputs, so the predictions. So eventually, when you end up at the bottom of a tree, we don't fork anymore. We just say like whatever we end up here, we're just going to make a decision. So quick question, what are some potential hyperparameters of this model? Yeah.
Maybe the number of internal nodes.
The number of nodes, yeah, that's a potential. Yeah, go ahead.
The maximum depth of the tree.
Yeah, maximum depth is a pretty natural hyperparameter. So yeah, these are different possible design choices we can make. So depth, maybe a number of nodes. And later when we're working with training data, yeah, go ahead.
Would the centimeter value be something that's a hyperparameter?
That's more something that we learn through the training process. So hyperparameter is something like we specify beforehand before we run the algorithm itself. Yeah. Up there?
Would the purity in the entropy of the inputs be a hyperparameter?
Would the entropy be a hyperparameter? Or?
Yeah, how would you
I think the way we specify it, usually entropy isn't a hyperparameter, but you could say like the choice of the loss we use, like how we measure how good a split is a hyperparameter. Well, yeah, we'll talk about entropy shortly. I guess the point of this question is just to keep in mind that there's different hyperparameters for different algorithms, right? So last week we talked about k nearest neighbors, so the main hyperparameter there is k. But in the case of decision trees, you can imagine many more different hyperparameters. Okay. All right. Yeah. So basically, decision trees, we can work with both classification and regression. The primary case we'll be focusing on today in lecture is classification, where we have to decide on between k different classes. Regression is like, remember, regression is a problem where you're supposed to output a real number, so this could be something like the house price. We'll mention like how you could do this with decision trees later as well, but we'll primarily be focusing on classification. And the way you decide on the output for a particular class is you'll notice that the decision boundary sort of splits our feature space into a bunch of different regions. The way we decide on what the label is or what the value is for that region for regression is you look at the training points that land in a particular region. So for example, if all these points landed up in this region and the majority of the points were oranges, then we would say that if we get a test point that also follows this criterion, we'll just assign it the majority class. So we just say it's an orange in this case. Okay, so the leaf values are like the labels we actually end up assigning. Okay. Here's just another example of a decision tree. So in this case, rather than having continuous features like we had before, we have discrete features. So this is like a example of a decision tree where you're trying to decide whether or not you're going to eat at a particular restaurant. And you can imagine a bunch of different features you consider when you're thinking about this problem. So whether or not there are other people, how long you have to wait, and so on. So eventually, by tracing through the answers to each of these questions, you arrive at a leaf node, which is a natural answer. So this is like one nice thing about decision trees is that they're pretty interpretable, right? We, as humans, often have this decision-making process, and we're just trying to formulate this in the form of an algorithm. Any questions? Yeah.
Do we manually determine like how to branch?
No, we don't. So we'll soon talk about how you go about designing this automatically. But yeah, I guess that's a key difference in machine learning in that we don't specify the logic ourselves. We just specify an objective, and then we learn the branching process through the data. Here's an example, which I guess you can potentially run through later. But this is just saying, if we have a bunch of training data, so I guess these are different data points, and these are our labels. If you run through some of them, you can end up seeing that if you run through this previous decision tree, you'll end up at least given decisions. But I think this part should be relatively intuitive. Like we just answer each question and follow our way down the decision tree. Okay, so some more properties about decision trees. So these are something that we call universal function approximators, which means they can approximate any function that we want. And you can sort of see this in that you can split each point at any boundary we want, so we can really construct any exact split that we want. But this isn't particularly useful to us if the decision tree doesn't generalize, and actually finding the smallest decision tree that correctly classifies a training set is NP complete, which if you remember from an algorithms class, it means it's like a hard problem to do. We don't have a simple algorithm to check this quickly. So the natural question is, how do we actually go about constructing a useful decision tree, which will be the bulk of the lecture. So the typical thing we actually do is we resort to something called a greedy heuristic. So this is something you've probably heard about before, which is saying that rather than try to figure out what the whole tree is all at once, we just try to make the best decision at every possible layer. And then after we make that decision, we make our splits, and then we make another decision. So at each step along the way, we have some metric that we're measuring, and then we make the best possible choice for that metric. In this case, we also introduced this concept of a loss. So this is the metric that we're optimizing to measure performance, basically. And this is done in the form of some scalar real number, where a loss value, if it's low, it's good, and if it's high, it's considered bad. And then the next natural question is, what sort of loss do we want to use? So I guess to help motivate the choice of loss, let's consider the sample data set here. And we'll consider two possible splits. So if you have this data set on the previous page, and we consider two splits along the vertical axis, intuitively, let's take a look at these two splits and see which split we feel like does a better job of like separating the data. So this is the top level split in our tree. Who thinks it's option A? How about option B? Okay, so we're pretty evenly divided, but I claim that A is going to be generally better because the main reason is A already ends up separating two of the red points here, which is pretty useful. Like we can just say these red points are separated if we're just focusing on the split alone. Whereas if you look at B here, the two classes are sort of still mixed together, right? Like we still have some uncertainty of whether which of the classes is red or blue, or like on either side of the decision boundary. And we'll formalize this notion here a bit more. Okay. So this is the first question sort of in the math quiz that we had. The goal sort of when we're making decision trees is we want every example in the leaf to eventually have the same class, because that minimizes the amount of uncertainty we have. So if each class actually ended up in roughly equal amounts, that's bad, because we're saying, given these combinations of features, we're really not sure what's going on. So in order to try to avoid this, we want to look at the counts, and we use this to define a probability distribution. Then we can use this concept of uncertainty in the probability distribution, also known as entropy, to determine whether or not we like a particular split or not. So this is just one way to evaluate a split. It's the primary way we'll be focusing on, and we'll dive into a bit of information theory to explain what entropy is. So you may have encountered the term entropy before. It's often used in other systems to describe the amount of uncertainty. The concept we're using in this class is the one from statistics, which is a property of a random variable. So the entropy it measures the amount of uncertainty in a random variable, and we have a sort of motivating example here. So suppose we have a coin, it might be an unfair coin, and we flip it a bunch of times, and then consider a different coin that we flip a bunch of times. And these are the two sequences of flips. The question that the entropy is trying to express is like, how much uncertainty is there in each of these sequences of flips? So we can plot a histogram of the distribution of sequence 1 versus sequence 2. And basically what the entropy is trying to express is that this sequence 1 here has less uncertainty. And that's because like you're more sure that it's going to end up being 0 than 1, whereas the second sequence, it's more of a 50-50 chance whether or not it lands at 0 or 1. So to define this in terms of a probability distribution or probability expression, the way we compute the entropy is with this expression here. I think this is actually slightly unintuitive. So another way that's more general to express entropy is you sum over the choices in your probability distribution, and then it's P of I log 1 over P of I. So of course, log 1 over x is also minus log x, so you can also write this as minus I minus P of I log P of I. Okay, let me make this a bit more clear. Let's go up here. So in the case where there's just exactly two different classes to consider, you can see that this formula here is equivalent to this formula, right? Because we're just saying the probability of the second event is 1 minus the probability of the first event. So this is the more general term for the entropy. It's a measure of uncertainty. And the sort of a way to see why you might consider this to be a measure of uncertainty is traditionally information theory is concerned about how you can send information from one person to another person. So suppose we had 3 letters that we wanted to communicate to another person, and we only were able to send this through a bit channel that's 0s and 1s. So if we had like A, B, and C, and let's say A shows up 1/2 of the time, B shows up 1/4 of the time, and C shows up 1/4 of the time, then like this isn't important, super important for the context of this class, but it's like helps you understand why entropy is defined the way it is. Then a way we could encode this information is we could assign the code 1 for A. For B, we can assign the code 0, 1, and for C, we can assign the code 0, 0. And then when we're trying to send a sequence of letters, like A, C, B, C or something, then we just send the code corresponding to these letters. So we would send 1, 0, 0, 0, 1, 0, 0, right? And whoever's on the other end of the channel receives the numbers, and this ends up being uniquely decodable. So there's only one possible interpretation of the letters given this sequence. And the reason this motivates the definition is you can see that the most common letter, A, we use just a single bit to encode, like we use 1. So you can think of this as 1/2 times 1 plus like 1/4 times 2 plus 1/4 times 2. And that's like the average length, the average number of bits we need to use to encode a particular sequence that follows this distribution. So that's why the definition of entropy is the way it is. It's not like something we're just pulling out of thin air. Any questions so far on definition? Yeah.
This is about decision trees. So is it possible to classify any arbitrary feature using just access line boundaries?
I think so, yeah. But you might have to end up like splitting on the same feature multiple times. So it could be like a really ugly looking decision tree. But you could classify every training set that's actually separable. Any other questions?
When you're dealing with a classification problem in machine learning, you know that the algorithm isn't learning when the number of times it gets it right is equal to 1 over the number of classes.
Right.
Where does entropy fall into that part of the machine?
Right. Yeah. So we'll soon address this. Like you can sort of see that if we have a leaf node that has this distribution here, it's better than the one that has the distribution on the right because we're more sure it's going to be class 0, right? Mm-hmm. So basically the definition we're coming to is we want low entropy in our system. So if we plugged in the formula here, we see that this ends up evaluating to number 1/2, while the one on the right is 0.99, right? So lower entropy is what we want to bench.
Right, but if you were to give these data sets to a machine learning algorithm,
Yeah.
and it were to guess one class,
Mhm.
it would still get a higher, in the case with low entropy, it would still get a higher number of guesses than without having to train as much. Because if it just guessed 0, you
Yeah.
would still get like an 88% success rate.
Right, yeah. So, yeah, basically we want to end up having leads that have low entropy, so then it can guess correctly, as
Oh.
you can think of it. Yeah.
Is there some sort of like inherent part of this model that limits like that makes it so we don't create like a super deep tree that has a whole bunch of decisions essentially? You know how you described creating like a model where every point
Mhm.
has its own branch? Like,
Right.
it essentially meets that.
Yeah.
With the split decisions.
Right, yeah, so intuitively, like, that's a bad tree, right? So
Yeah.
you can specify as hyperparameters, like, the depth of the tree. So
Okay.
perhaps if you don't have too many features that you're not saying this feature has to be between these two values and then so on for each feature, then that's perhaps a better classifier. Yeah, and I guess the way we choose hyperparameters as a preview is we're going to use validation sets again. Okay. Right. So one of the most important conclusions from information theory is Claude Shannon, who basically invented information theory in one of his papers, is that you can't store the outcome of a random variable using fewer expected bits than the entropy without losing some information. So we sort of showed on the previous slide how you might go about storing a bunch of, or like coding a random variable. And units of entropy, when we're using log base 2, are called bits. A fair coin flip, which is shown here, has 1 bit of entropy. So this plot here is like showing the entropy of a given random variable. And we can sort of intuitively just describe like high entropy and low entropy distributions. So high entropy is when we have more of a uniform type distribution where more uncertainty about the outcome and it's less predictable. Whereas low entropy is when our distribution's more concentrated in just a few outcomes. It might be something like this, whereas low entropy is more uniformly distributed, right? Yeah, go ahead.
I was a little confused about the graph 2 slides before.
Uh-huh.
Is that the graph for one coin flip or multiple coin flips?
This is a plot of the entropy the way to think about this graph is we have a weighted coin, which lands heads with probability P.
Okay.
And then this is saying like if P takes on this particular value on the x-axis, what the entropy ends up being.
Uh-huh.
So if P is 1, there's no uncertainty at all, right? And our entropy is 0. Which is sort of a nice measure to have. Like when we're absolutely certain, our entropy is going to be 0. But if we're really uncertain about the outcome, like if the coin is flipped, if the coin is fair and it's flipped, then it's going to be an entropy of 1 bit. Yeah.
Does this have anything to do with variance or no?
There is no variance here. Yeah.
How did you say you calculated 1 bit again?
Yeah. It's just plugging it into the definition itself, actually. So you could do like 1/2 log 1 over 1/2 plus 1/2 log 1 over 1/2. So this is equal to 1/2 log 2. And since we're using like base 2, it's going to be equal to 1 exact. Yeah, question?
Can you explain again, like, what does the thing mean, like, where the entropy means, like, the number of bits?
Like explain this graph here one more time?
No, like, this thing on a below graph, like,
Yeah, this is saying like to summarize this probability distribution, like if you have to summarize 1,000 flips and send it to some other person, then what's the minimum number of bits you need to send? So I don't think we need to fully understand this concept because we're not like teaching information theory in particular, but just like the definition of entropy itself should make sense. All right, so the way we're going to end up using entropy is we have some potential split. We want to basically evaluate the entropy after performing the split and figure out how much the entropy changed, right? And that's the definition we're working towards. So we're trying to figure out the expected reduction in our uncertainty about y after observing x. So basically you can think of y as like our initial distribution of labels. And then x is like a split that we're considering. This could be, in the earlier case, like the height, whether or not it's less or greater than.
What are the units of, right, then what are the units of x in a way?
What are the, we're,
Are the units of x and y the same? That's the question.
right, yeah, we're going to be measuring entropy always in bits. So, but I guess x here we're just referring to as an event of a split. So I guess to be a bit more concrete, let's focus on this particular example where we have a joint distribution of whether or not it's cloudy or not and whether or not it's raining. And you can imagine various probability distributions here. We can evaluate the entropy of a joint distribution as well with the same sort of definition we had before. It's also just going to be equal to the probability times log of the probability with a negative sign in front. And you can plug in the numbers from this distribution to end up with an entropy of this cloudy, not cloudy, and raining, not raining concept, right? Yeah.
And so on average, to describe the weather, we would have to send 1.56 bits.
Yeah, this is what the information theory interpretation is.
Okay.
Yeah.
And then it would be like cloudy's 0 and not cloudy's 1, and then raining's, or like cloudy and raining are 1 and 0, and
Yeah.
not cloudy and not raining is like 0.
Something like that. Yeah, the actual way to design a code is beyond the scope. Like if the numbers are nice powers of 2, there's a nice way to design the code. But if they're uglier numbers like leaves, it's a bit more complicated how you design a code. Yeah.
What exactly are we trying to figure out when doing this?
Yeah, we'll get there. So.
Like, what are we trying to decide?
Oh, in this case, I guess like you're trying to decide whether you're bringing an umbrella outside or something. Yeah, I guess the particular motivation isn't super important for this problem. We're just mechanically working through an example of how to compute entropy. So I guess this example sort of does make sense in that if it's raining, it's a lot more likely to be cloudy than not cloudy, whereas if it's not raining, there's still a slight chance it's cloudy, but more likely than not, it's not cloudy. So there's also this concept called the conditional entropy, which is if you're conditioning on a particular value of a variable, what's the entropy of another one? The way we define this is entropy of y given x takes on a particular value. So let's say we want the entropy of cloudiness, y, given that it is raining. So that means we're focusing on this particular row here. And we're using the conditional distribution. So probability of cloudy given raining. Remember from our review, this is using Bayes' rule. So we want the probability it's raining in the denominator and probability it's cloudy in the numerator. And to be explicit here, probability it's cloudy is 24 over 100. Probability it's raining is the sum of all the entries in the row, right? So it's 25 over 100. So we get 24 over 25. Similarly, we can find the probability it's not cloudy. That's going to be 1 over 25. And then when we're saying conditional entropy, we're saying like conditioned on the fact of another random variable, what's the entropy of the resulting distribution? So you can just think of it as you're going to plug this distribution into the formula from the previous slide. Right. So this is our probability of y given x, and then we can calculate out the numbers. Yeah.
Do we always use log base 2?
Yeah, we're going to use log base 2 in this class. Yeah.
Okay, so for entropy, for example, for like the coin example, we had heads and tails. So that's like two kind of outcomes. If there's like more than like two outcomes, for example, if there's like 3 or more, how do you calculate the entropy for that?
Right. Yeah, it's the same general formula. It's going to be sum minus p of I log p of I over the different possible outcomes I. Yeah.
Should the numerator be the probability that it's cloudy and raised, or just
Oh, sorry. Yeah, you're right. Yeah, this is probability cloudy and raining. Yeah. Yeah, I wrote the correct thing on the next step, but yeah, good catch. Any other questions? Yeah.
All right, so the goal is that every time we traverse a label, it should say that something's given, right?
Mm-hmm. Yeah. There's also the concept of expected conditional entropy. So this is like, we're trying to figure out what the expected entropy is given knowledge of an entire random variable. So here, we focus on one particular instance of a random variable, right? Like we're focusing on x equals cloudy. Here, we're just trying to figure out, like, if you know what x is, like it could be cloudy or not cloudy, then what's the expected entropy? So to do this, we have to figure out for each outcome x, what's the probability x takes on the value of x, and then the entropy given that choice of x, right? If you expand out this equation here, entropy of y given x equals x. Remember, entropy is the probability y equals y given x equals x times like the log probability y equals y given x equals x. And then there's like a minus sign in front here, right? If you end up combining the two terms on the right, we have like a probability x and probability y given x. These two terms combine into probability of x equals x and y equals y. So that's why you get the joint probability of x and y here. And then we also still have this log term. So the expected conditional entropy ends up having the joint distribution times this log conditional distribution. It's a little bit more clear, I guess, if we work through this example for the raining case. Yeah.
It seems like you're saying that the conditional entropy is equal to the expected conditional entropy. That you're trying to say.
I'm just like writing out the
Because the slides seem to imply that.
Yeah.
So is that the case?
Yeah, I guess there's like two different concepts here. Like there's the general conditional entropy, which is saying given knowledge of the random variable, like we don't know, like it could be cloudy or not cloudy, but if we know whether it's cloudy or not cloudy, then what's the entropy is. Or you can say like given a specific instantiation, like given that it is cloudy, what's the entropy? So you can both refer to both as the conditional entropy. They're just slightly different use cases. So the way we're going to use this is like, what is entropy of cloudiness given the knowledge of whether or not it's raining, right? So you want to figure out the raw probabilities it's raining or not. So this is going to be 1/4, and this is 3/4. And the way we calculate the conditional entropy in this case is we want basically 1/4 times the entropy, it's cloudy, given it's raining, plus 3/4 the entropy if it's cloudy, given it's not raining. Does that make sense? Yeah.
Sorry, where does the 1/4?
Yeah, the 1/4 is from 100 plus 100. Right. So we're looking at we're marginalizing essentially over one variable and figuring out how much information it's giving us, or how many bits less we need. Okay. So the reason this comes up useful is we can usually decompose joint entropies into conditional entropies and single entropy quantities. So there's this idea of a chain rule, which is entropy of a joint distribution is going to be equal to the sum of the conditional distribution plus the single variable. And we also know that entropy is always non-negative. Just by the definition, it's going to give us a non-negative number. So essentially what this is saying is, because we know that if one property that we get from this sequence of equations is that entropy only decreases when you're given knowledge of a new variable. So entropy of y given x is always going to be less than or equal to the entropy of y itself. And the way we basically quantify how much information we gain when we're doing a split, so sort of moving back into the realm of decision trees, is we're figuring out how much uncertainty decreases when we're given knowledge of this new random variable. So this is called the information gain. And the way we calculate the information gain of a particular random variable is by measuring the difference in entropies. So we want the entropy of the initial distribution followed by the entropy after the split. And this is how we measure how much information changes. So this is the number that's always greater than or equal to 0. And the information gain is 0 if it's saying that x is completely uninformative about y. So we don't gain any knowledge about x after knowing y. If it's completely informative, the information gain can actually be equal to the entropy of y itself. So if the split perfectly separates out two classes, then the information gain is maximized. Like if we initially had 10 lemons and 8 citruses, 8 oranges, then if we separate them out completely, the information gain is the entropy itself. Yeah.
When we see completely informative, it means that that h of y given x is 0, right?
No, completely informative means that.
No, h of y given, yeah, right.
It means that the h of y given x is equal. Wait, hang on. Yeah, it's completely uninformative means that you don't gain any new information from the variable. Completely informative means. Wait, let's just write this out to be clear. So, are you worried about the second case or the first case?
The second case.
Yeah, okay. So in this case, we know information gain is equal to h of y. So we have h of y equals h of y minus h of y given x. So in this case, h of y given x is equal to 0. So this is saying that given knowledge of x, there's no more uncertainty in y. So all the uncertainty in y is gone after you know what x is.
So that means that in this case, where you're completely informed, the two events would be, or the two classes would be mutually exclusive.
Yeah, after the split, the two classes are mutually exclusive. Yeah. Okay, I think we can finally circle back to decision trees now. So information gain basically measures the informativeness of a variable, which is what we want when we're considering possible splits in decision trees. Remember, we're trying to go back to using our data to decide which splits we want to consider. And the information gain just tells you how much information you're gaining. So we're trying to pick splits that maximize our information gain. If we revisit the example that we touched on earlier, you can consider the information gain from the two different splits that we considered before. So this is a split that we said was not quite as good. And the reason that is we can consider the entropy before the split. So initially there's 2 blues and 5 red dots, right? So the initial entropy is just calculated with this expression. That's the definition of entropy. And then after the split, we're going to end up with 2 separate instances. We're either going to have 1 blue, 3 red, or 1 blue and 2 reds. So this is where all the conditional entropy stuff we did in the previous slides actually comes back together. The probability we go down this branch is 4/7, right? And the probability we go down this branch is 3/7. And then you want to figure out the entropy of this distribution here. So entropy 1/4 and 3/4. Plus the 3/7 entropy 1/3, 2/3. So that's basically what the conditional entropy is given the split. So if we evaluate this expression, this comes out to actually around 0.81. This is around 0.92. And in total, this doesn't give us very much information as measured by entropy. So the information gain of the split is around 0.006, which is not very informative. Yeah.
What is y here?
Y is the split we choose. So I guess in this case, it's whether the width is greater than or less than a certain number. Yeah.
Yeah, where's 2/7, 5% come from?
Where is 2 and 5 come?
Where does the 2/7 and 5/7 in the slides come from?
Yeah, that's the initial distribution. So initially we have 2 blues and 5 reds.
Oh, right.
So, right. Yeah, so the way to think about decision trees and how we're considering splits with entropy is you figure out what the initial entropy is, then you consider some sort of split, figure out what the conditional entropies are for that split, and then if you calculate the expected conditional entropy, you can figure out how much information you gained. Yeah, question?
So in this, in the earlier example, this one. Why would the random variable y would be, how accurate we are predicting which one is which, and then random variable x is which side we're on the split.
Yeah, so I think in this case you should think of y as the distribution of labels. And in general, that's true. It's the distribution of different classes that we have in that particular node. And then the split, whether we go left or right, is some sort of rule, based on the continuous features that we have, or discrete features. So in this case, going right might be x1 might be the width is greater than 10. Let's just use like arbitrary units. And then x2 is width less than or equal to 10. So this is like left, and then it goes right. So x is like the specific rule that we're choosing. Yeah.
And information gain is also in bits, right?
Yeah, it's also in bits. Yep. Cool. Any other questions? Yeah, go ahead.
How is H of Y given the calculated to be ratio?
Wait, sorry, what?
Alright, what values are used to calculate H of Y given left?
Yeah, h of y given left is we're using the 1 blue and 3 red values. Whoops, sorry. So this corresponds to distribution 1/4 and 3/4. Remember, we're turning like the number of counts into a distribution, and we're figuring out what the entropy is.
Or does it matter if it's 1/4, 3/4, or 3/4, 1/4, or does it not matter?
It doesn't matter because it's the sum, so it doesn't. The order doesn't matter. Yeah. Question.
In this situation, something that was like a diagonal boundary line
Yeah.
would be better, but that would rely on both. Would that rely on both height and width?
Yeah. Yeah.
And in that situation, would you need to create like a matrix of entropy values and normalize them to find what the entropy should be?
Right. Yeah. We aren't gonna cover that in this class, but I think you can have more sophisticated stuff. The nice thing about focusing on just one feature at a time is there's like more computational efficient ways to look at all possible splits, basically. So you can consider this split and figure out their information gains relatively quickly. Yeah.
Is there a word that, because there's multiple ways of choosing the vertical line such that it splits the two on the left
Yeah.
and on the bottom right? Is there like characterizing an optimal one or best one, and just adding more points to the training set?
Yeah. So in general, like trying to find like the best possible setup for decision tree, that's a really hard problem. So I don't think there's an easy solution. Okay. So yeah, let's move on. So in the case of split A, where we split on width of list value, the main takeaway here is that the original entropy is still going to be the same. It's the 0.86 from the previous slide. But here you'll notice that the entropy on the left is actually going to be 0 because there's no more uncertainty on the left branch, while the entropy on the right is it's 2/5 and 3/5. Right? You use the entropy formula on these two values. And then if you evaluate the information gain in this case, it's a lot bigger. It's actually going to give us 0.17 bits of information. So if you're just making one split on this tree, we're saying that it's a lot more effective to choose split A. Yeah.
So when you're talking about H25 and 35, so does that mean like 25 and 35 are two different random variable values?
2/5 and 3/5 you should think of as it's the probability distribution defined by the labels. Right. So because there's 3 reds and 2 blues, we're saying the distribution is 3/5.
Right.
Yeah.
But then earlier when we had like when we were talking about like H and two variables, like those are like two different things.
What do you mean?
No, I mean if you go down.
Yeah.
So we're talking about H, Y, and I guess splits. And then so I was thinking like the H on top is different from the H on the bottom, right? Like it's talking about two different things.
I guess they're both measuring entropy, but one is like conditioned on a certain knowledge of the width, basically.
Like the one that you wrote on, if that was where the uncertainty about like if you pick one, which one you're going to pick, and but then the bottom one is like where you're going, right?
Yeah.
Okay.
Yeah, maybe we can clarify during the break if it's still unclear. Yeah, we'll take a break in like 10, 15 minutes or so, maybe. Okay, so yeah, go.
Any constraint for the split itself?
There's, in general, no constraints on the splits. Like, we should consider all possible splits. But intuitively, I guess, you want like a split that gives you information gain. So the basic way to run the algorithm is what we'll describe, actually. So to actually go about constructing a decision tree, so let's suppose...
Is it arbitrary?
Sorry?
Is it arbitrary?
It's not arbitrary. Like, we're going to use our data and then this information gain metric to decide how to construct the decision tree. Okay, so back to the running example, like how do we actually construct a decision tree? So here we're given a bunch of data, right? And the way the algorithm works is that each level you want to consider all different features and all different possibilities on where you could split that feature. Then you evaluate the information gain from every single combination, and then you choose the feature and the split along that feature that gives the maximum information gain. So this is the default algorithm for decision trees that tends to work pretty well just out of the box. Here's a more formal like algorithm sort of statement. So you're starting from your root node, and then you pick a feature to split at a given node, and then you split examples based on this feature value. If the way this algorithm converges, if there's no examples left, then we're done. So we just return the majority. If it's all from the same class, then we're also done. Otherwise, we just keep repeating this algorithm. So we treat the next node down as the root node, and then we also consider all possible splits. Yeah.
In the previous slide, you mentioned that the way we get to the thing that gives us the most information gain is by trying every different combination.
Yeah.
How do you do something like that when you have a continuous feature like?
Yeah. So I don't think we'll ask you to implement a decision tree like on homework or anything, but intuitively how you would do this is if we have, let's say our feature 1 was something like, we would sort the values, and then to consider all possible splits, you just like look at any time there's a change in the values. So you would consider this split, that's split 1, 2, and then so on, right? And you can sort of see there's like a quick way to check like what the labels changed between these two splits. Like if to go from split 1 to split 2, you just have to look at what the label of 3 is, and then we can update our counts quickly.
So what does same class mean?
So we're focusing on classification. So this is saying like if everything is a lemon, then we're done. Like that node is done, and we don't need to split anymore because it's.
How does that look like?
How does in a decision tree of a particular node, if it's like 8 lemons and that's the only training data you had that followed like these height and width parameters, then that means we're done. Okay. Yeah. Actually, maybe it's a good time to I'll take this question and then we'll break. Yeah.
So this algorithm will eventually get everything to entropy 0 on the roots.
Yeah, eventually. I guess it depends on your hyperparameter. Like you have to decide how long you want to run the algorithm, because you can imagine like with nearest neighbors, if you run it for a long time, you'll get a really complicated decision boundary, which might not capture the underlying pattern. Okay, yeah, maybe let's break here because it's a natural stopping point and resume at 12:15.